Hello, everybody. My name is Masood Olia, and I'm a faculty in the School of Engineering at Wentworth Institute of Technology. And I'm here with an example of how we can use method of sections to determine the forces in selected member of a truss. So as you guys know, there are different ways that you could, solve for forces in different members. So one is called method of joints, which is a very tedious way of figuring out forces, and usually you do that when you want to figure out forces in almost all the members of a truss. And the other method, which is in a way a shortcut, and you do it when you are only interested to figure out forces in selected members, is called method of sections. And that's what I want to show you here. So I want to use method of sections. So what I'm going to do, guys, I'm going to remove my picture so we can actually, so let me go ahead and stop my video, and I'll go back to my OneNote. So this way I can, flatten my, sorry. Right. So method of sections, guys, is our the way we want to solve this problem. And what I'm trying to find, actually, I want to find force in selected members. So I'm going to highlight this for you. I want to find the force in member BD, in member CD, and in member CE. So I want to find force in members, as I said, BD, CD, and CE. And as you know, as we solve for these forces, we can then determine if they are in tension or compression. I'll show you how you can figure that out very easily. All right, so in method of sections, what you want to do is you want to look at this section where your forces are, and you can cut through members. You don't want to cut, the general rule is that you don't want to cut more than 3 members at a time. And but that's just the general rule. So you can cut, at an angle, you can cut it straight. So for example, because these 3 members are right here, I'm going to cut the truss like that. Then you have to ask yourself, do I need to figure out the reactions at the pin here and the roller here, E and F, right? And because you see, you have the choice of using the left portion of your free body diagram or the right portion of your free body diagram, whichever is more efficient or convenient. So it turns out that in this case, it's more efficient for me to figure out the forces by using the left side of the free body diagram. So in other words, I'm going to now just look at the left side and show you these forces. Oops, if I get my pen in order here. Here we go. So I'm going to have a force in member FE. And actually, let me go ahead and redraw this free body diagram. Anyways, I think it's a good idea to do that. So by left side, I mean, we want to just concentrate on this side, right? So we do have a force. And look, I'm going to take this 130 and notice that conveniently 130 times 5/13 becomes 50 pounds. So break it into 2 components, and 130 times 12/13 becomes 120 pounds. All right, and now look, guys, where I cut right here, I would expose force in member BD, force in member CD, and force in member CE. And remember now, why did I show these forces always pointing away from these joints? The joints are B and C here. Because if you show them as if they're pointing away, you're assuming that they're in tension. If you solve the problem and you get a positive answer, that means the member is in tension. And if you end up getting a negative, that means the member is in compression. That's the easiest way that you can figure out which member is in tension and compression. So that's how we're going to do this. So remember, as I said, you don't want to cut more than 3 members at a time, because you don't want to have more than 3 equations, because you're treating this left side of the free body diagram as a rigid body. And for a 2-dimensional rigid body, remember, we have 3 equations. So remember, you don't want to have more than 3 unknowns in general. So these are the equations that we have to use. And look, the method of sections, I said, is a shortcut. The way you use method of sections, you want to take moment about a point. So you want to actually use your moment equation as much as possible, as many times as possible. You can actually say, okay, let's say I want to find the forcing member BD, right? So let me go ahead and take moment about a point where these 2 guys don't have any moment, meaning FCD and FCE. And that point would be point C, because they're going through C. So by taking moment about C, I can go ahead and find the forcing member BD. So let me go ahead and call this a positive direction. So look, guys, I'm taking moment about C to the moment of FBD about C. Remember, dimensions are given. So this is 4 feet and this is 3 feet, right? So that would be times 4. It's going clockwise, so I call it negative. Then I have the moment of 50, which is going counterclockwise, also times 4 feet. And the moment of 120, which is also going counterclockwise, times 3 feet. So if you go ahead and solve for FBD, we get a positive answer for FBD, and I believe it becomes, let's say, 200 plus 365, 60 divided by 4, that's 140. So you write your answer like this, 140 pound, the unit. And because you got a positive answer, you say that member is in tension. All right, so now you got the idea. Now, let's say you want to find now the forcing member CE. Oops, I picked up my pen. I wanted to actually say forcing member CE. All right, so take moment, if you want to use your moment equation, take moment about a point where these 2 other forces are intersecting. So you can actually take moment about, you see this, how these 2 guys are intersecting at point D here. So that's the efficient way of solving this problem, by taking moment. I mean, for member C, take moment about D, say it equals 0. Again, let's say counterclockwise is positive. So that leaves just FCE, right? Times what? Times 4, going counterclockwise positive. And then notice that even the 50 pound here, this 50 pound passes through D, doesn't have any moment. So that leaves 120, which is going also counterclockwise, times, looks like 6, right? So that's equal to 0. So FCE comes out to be what? 180 negative, right? Well, because we get a negative answer, what do we say? Because a negative, that means the member has to be in compression. In other words, the force has to switch direction and point towards C. So 180 pound, and then you write your answer as a C compression. And then guys, look, you don't have to always use the moment equation, right? You can use the other 2 equations. One equation, by the way, if you want to follow the concept of moment here, you want to say, well, no, this is the only one that is left, FCD. But you see, you cannot find a point where these 2 guys, CE and BD, intersect, because they're parallel. So why don't we just go ahead and use even though you can use a moment equation about some convenient point. But actually, in this case, you see, since CD is the only force that has a Y component, and of course I have the 120 external load, why don't we just balance forces in the Y direction? And that's the quickest way to find FCD. Notice that I have the slope of this guy is 4/3, right? Based on the dimension that we have, right? So the Y component of FCD is 4/5 of FCD, going positive, or I think it's positive. And then 120 going down. So FCD happens to be a positive number, which is equal to 150. 150, and notice that because we got a positive answer, this guy is in. So I hope you guys like this video. I would come, I'm gonna put my picture back, and I want to go back to the OneNote. Here we go. So guys, thank you for watching and listening. As always, if you like the video, please leave any comment you have, and like the video and subscribe to my channel, and I'll frequently come with new videos on different topics, you know, vibrations, statics, mechanics of materials, dynamics, and so on. Again, as always, thank you, and I'll see you guys soon.